So last time we discussed the possibility that the solution may not exist. So right now we have some theorems that shows if a solution exists in some initial conditions or not. So to understand those theorems, we have to understand what an initial condition, and we take it against something called a boundary condition. So an initial condition is a condition at a specific point. So imagine if you have f of x naught equal to something. This is always an initial condition. In terms of first order ODE, there is no obvious difference between initial condition and a boundary condition. So we need at least, so for those stuff to exist a unique solution, we need, if it was a second order differential equation, we need two initial conditions, or two conditions. We call it two initial conditions. With third order, for those three theories that we can discuss, we need three conditions, or three initial conditions. So for the first thing, does not really matter. Once we go to the second derivative, so imagine second derivative, so we go to something is equal to c1, some value, and x naught is equal to c2. This is two initial conditions for those theories to work. Because the second order differential equation, we need two initial conditions. So this is the initial condition, and this is the initial condition. So initial condition is a condition that's specified at a specific point, and we know the value of the function at that point. The value O is derivative. So again and again and again. So what's this thing all about? Imagine if we have a first order differential equation. This is a first order differential equation. We want the initial condition. We know the initial condition gonna be a least degree from 1 degree less than the highest order. So we know that it's gonna be in the shape of f of x naught is equal to c1. If we have a second degree differential equation, we know it's going to be in a form of a degree less than this thing. So it's going to be f prime of x naught equal to c1, and f of x naught is equal to c2, and we must have at the same point. It must be at the same point, and we call this thing as an initial condition. For the boundary condition, it's different. So we have something that tells us about the system, about the solution of the system, but at two different points. So for first equation, is if we call this thing is initial I, and I, this is the first differential equation, the second differential equation. For first order, there's no difference between initial condition and boundary condition, so you won't go through it. For the second order differential equation, it can be in the form of f of x naught is equal to c1, and if f of x naught prime is equal to c2. In other words, this can tell us something like f at 3 is equal to 6, and f at 4 is equal to 5. This is a boundary condition because f of this thing is different than that thing. It can be also a boundary condition as f prime of 3 is equal to 6 and f prime of 4 is equal to 5. This is another boundary condition. So this is a type of boundary condition. So the initial condition, you see that the equation, okay, this is like third order differential equation. So how many initial conditions it's gonna be? It's gonna have two initial conditions. f prime and f. Fifth order for f to the f, the fourth derivative, the evaluated at some point, third derivative is evaluated at the same point, second and the first and the function. So there's four of them, four of them with a fifth degree. Oh, actually, there's actually five of them is a fifth degree because you include the zero. So if the number of initial condition will be equal to the number, so the number of initial condition will be equal to the number of the order of the differential equation. First order, one differential equation, one initial condition. Second order, 2, 3. Third order, 3. Fourth order, 4. Nth order, n initial conditions. Why is this important? Because this is also one of the terminology that we have to understand to differentiate between an initial condition and a boundary condition. So initial condition evaluated at the same point, boundary condition evaluated at this different point. This is also again, as I said, this is also a boundary condition. So this same point, initial condition, different point, boundary condition. So let's go and see some theories that talks about existence and uniqueness theorem. The first theory is a local statement or a local theory. It tells you that, imagine this is a differential equation, this is a differential equation. So far we're gonna only deal with the first order differential equation. For the next couple of videos it's gonna be only for the first order differential equation. So let's focus on things like I. Imagine if we can separate the first order differential equation, we can write it as a function of first order differential equation, we can write it as a function of phi prime y and x is equal to 0. Any first order can be written as this in this form. Imagine if we were able to separate y prime and put it as some function of g of phi and x. So imagine if we can solve this equation algebraically and we find the y prime as a function of y and x. For example, in the first in I, we can write y prime dy dx, or y prime is equal to negative 6x. So we actually separated the prime thing into something like y something prime is equal to some function. And we're talking about initial condition. This theorem we talk about initial condition, and we say what's an initial condition. Why we could say the first order does not matter, but in higher order things does matter. So right now we separated this thing into, so the general thing that we can separate the first order as a function of g and x. So the theorem says to you, let's write the theorem here. This is the first existence and uniqueness theorem. This theorem is kind of not complicated, but it's kind of a little bit not good, little bit bitchy. So imagine if we can write y prime as a function of g of y and x. This is, so right now we separated it and we could write y prime as a function of something of g and x. So okay, take this function and take the partial derivative with respect to it. X to get another function. Let's go to h of x. F(x) and maybe and also y, it depends. So we get a new function by differentiating this thing with respect to x, and take this function again and this differentiate it with respect to y, and let's call this function as m of x y. So far, the theorem says, okay, you have first order, right? Let's try to solve it. To try to solve this first order, not like solve the differential equation, just try to separate the first order. You separate the first order, you get some function of x and y, because the original function was of x and y prime. You solve y prime, you get a function of x and y. This function, if you take the partial derivative with respect to x and take the partial derivative with respect to y, you have the initial condition. You have the initial condition as like, you have the initial condition that y at some value of x is equal to some value of y prime. So we know that you have initial condition. For example of this, let's say like, if you know that y at 3 is equal to 6. Okay, so you have this, it's like, what that symbols means. Like, yeah, they give you some, the problem, the physical problem have some value of x, like at this point, the value of the function would be equal to capital Y. So for example, y of 3 is equal to 6. So far, we did this stuff. You go to the function of what h of x and y and ask yourself, is this continuous at capital X and capital Y? In other words, the value that gave you for x and y. You go and ask yourself the same question for m of x and y. Is this continuous at capital X and capital Y? If the answer was yes, then the theorem tells you that there exists the first part of the theorem is the existence, a unique, second part is the uniqueness, solution in the interval of x minus capital X that lies between some a and some negative a, and y minus y prime that lies between some value of b and negative b. So okay, the theorem say okay, that thing does exist. There's a unique solution for this. Then okay, say okay, that's cool. There's this unique solution, and then okay, there's this unique solution. Okay, so the condition, all the condition has been satisfied. Right now, it tells you okay, you can either in this vicinity or next to this point of capital X and capital Y. This means next to the point, and this is A. So for some value of A, so this is the interval. This is like next to it, and this also next to it. For this thing means you can I'm gonna see into one of them what this interval actually means. First, and this is good. This is told you for some value of A and B. So let's take one of the intervals if the interval seems complicated. And take just the bigger sign. And we say this is for when we not want the A to be positive, for some A and B positive, for some value of positive A and B. So the A and B must be positive. So from this equality, from first equality, they told you okay, you can walk a little bit in the positive direction. And from the second one, they told you can walk backward a little bit by A. So for this thing, you can either walk a little bit forward or you can walk a little bit backward. Let's just draw a diagram that sees this thing. Is it square?